Okay, we're going to be learning lesson 6.1. You want to say hi? Ah, there we go. Okay. All right. So for starters, polygons. A polygon is a closed plane figure with at least 3 straight sides and angles. So closed plane figure, plane meaning endless flat surface, right? So a plane is flat, does not have 3 dimensions. It's just a flat thing. At least 3, so it's going to be a triangle or more, obviously. And it has to be straight. So is a circle a polygon? No, a circle is not a polygon. Anything with a curve is not going to be a polygon. Interior angles, exterior angles. Okay, we've talked about this before. It's, I think, pretty self-explanatory. Interior angles are on the inside of the polygon, and exterior angles are on the outside. Now, exterior angle is formed by extending a side and then creating the linear pair with the interior angle. So if you remember, we did the triangle exterior angle theorem. Do you remember that? This exterior angle was equal to the sum of the 2 remote interior angles. Remember that one? Yes, sort of. Okay. So we talked about exterior angles when we learned that. But here we're looking at a polygon where there's all these exterior angles. If you drew them all at the same time, that's when we get the sum of the exterior angles. Okay? That means all of them at the same time. There's 2 types of polygons, convex and concave. We are only really going to be dealing with convex polygons. So convex polygons are polygons that you're used to, the ones that you've seen, the normal ones. Okay, a concave polygon basically looks like somebody punched it in. It's like has a dent in it. By definition, it has an angle that's greater than 180 degrees. So it's like overextended angle. Sometimes people remember it because it looks like a cave. Right? It's pushed in. Kind of looks like a cave, so concave. But like I said, all of the formulas and the stuff that we're going to be doing is always going to be dealing with convex. So you just really need to know that concave exists. Equilateral, equiangular, we've talked about before, right? Equilateral, all the sides are congruent or equal. Equiangular, all the angles are congruent or equal. Regular combines the 2. This is a really important term. I think it's one that's easy to kind of look over and not realize how important that word is. We're used to regular meaning like something not very special, right? Like, oh, it was just a regular old day. It was just, you know, a regular old whatever. But a regular polygon is actually really special. It's got all the sides congruent and all the angles congruent. Okay, so you don't want to just pass over the word regular as if it's inconsequential. It's actually really giving you a lot of information. All the sides are congruent. All the angles are congruent. Okay? Diagonals of a polygon. You've seen diagonals before, probably mostly in a rectangle or a square, right? You can draw the diagonal. But by definition, it's a segment that connects 2 vertices, and it has this word non-consecutive vertices. Remember we talked about consecutive, one right after the other, right? Consecutive days, consecutive, whatever. One right after the other. So vertices that are consecutive are going to be this one and then the very next one, right? So if you draw a segment between 2 consecutive vertices, is that a diagonal? No, that's just the side. So diagonals are the non-consecutive vertices. You go from one vertex to another that's not right next to it. In these 2 scenarios, both of these, this quadrilateral square and this octagon, have all possible diagonals drawn. Look at the octagon has 20 diagonals, okay? But sometimes we can just draw the diagonals from one vertex, and this is going to be what we do next to kind of derive our formula. So just from one vertex, this hexagon, there's 3 diagonals that can be drawn from each vertex there. Okay, let's look at the other side. And we're going to be filling out this chart. The sum of the interior angles of a polygon is our goal here. We're trying to find the formula for figuring out what the interior angles of a polygon add up to. We already know triangle. What do the three angles of a triangle add up to? 180 degrees. Good. So sum of the interior angles right here for triangle is 180. We already know that. Let's name these though. All of these are organized by number of sides. So a triangle has 3, and then these just go in order. Oops, mine's already there. Okay, and they all have special names. 3 is obviously triangle. 4 is quadrilateral. Okay, so they all have these special names. Just want to make sure I get this on the video. 10 sides is decagon. 12 sides is dodecagon. Anything beyond those that I just listed here, we're just going to call them whatever the number is, gon. So like if you have something with 23 sides, it's going to be called a 23 gon. 23-gon. And that's what, I didn't make that up. That's actually what they do. So like for 11, there is a special name, but it's not one anybody knows. Just call it an 11 gon. All right? So you'll see it, excuse me, written that way sometimes. Okay, so back up to here. The task we have here is to draw the the diagonals from one vertex and see how many triangles are formed. Why? Because we know the interior angles of a triangle add up to 180. So we're going to use that to figure out the rest of these. In a triangle, if I start at one vertex and draw diagonals, how many diagonals could I draw? None. Can't go to, the only vertex to go to is a consecutive one. So there's no diagonals here. So there's just one triangle in this diagram. But let's look at quadrilateral. From one vertex, I draw a diagonal. How many triangles are formed? 2. 1, 2. Well, if we want the sum of the interior angles of this quadrilateral, we could use the fact that these 3 angles add up to 180, and these 3 angles add up to 180. Because together, this angle plus this whole angle plus this whole angle plus this whole angle will give us the sum of the whole quadrilateral's interior angles. So it's just going to be 180 and another 180. So what's the sum of the interior angles of this quadrilateral? 360. Now this last column is asking for the degree measure of each interior angle if it's regular. So if we know all the angles are the same measure, if they all add up to 180, what's each angle going to be? 60, because we're going to do 180 divided by 3 equal angles. Gives you 60 degrees each. For this one, they all add up to 360, and there's 4 of them, so each angle would be 90 degrees. Now, we can continue with this same task here. Draw the diagonals of a pentagon, and how many triangles are formed? 1, 2, 3. So how are we going to get the degree measure for the sum of the interior angles? What do you think we're going to do here? Yeah, 180 times 3. Here, I should add this here. 180 times 2 triangles. Here, it's 180 times the 3 triangles. And that gets you 540. So to get each angle measure, what are we going to do? 540 divided by 5 sides this time, and each angle is 108 degrees. Okay, now we could keep going with this, but do you see a pattern? How many triangles are going to be formed with 6 sides? What do you think the number is going to be right here? 4. Right, we've got 1, 2, 3, 4. This one's going to be 5. This one's going to be 6. That one's going to be 7. Let's look at the last row here. A regular n-gon, we're going to say, has n number of sides. What expression could we write here in terms of n for the number of triangles formed? What's the pattern from this column to this column? What do you do every single time, Lauren? N minus 2. It's always 2 less. And then in this column for getting the sum of the interior angles, we always did 180 times the number of triangles. So if the number of triangles is n minus 2, that's how we get our formula for the sum of the interior angles of a polygon. Each interior angle, we're going to just take the sum and divide it by the number of sides. First of all, stars and box or circle or whatever, there's your formula right there. That is the most important piece of information on this front side of this piece of paper. Okay? From this whole lesson, everything comes down to this formula and the exterior angles, which we're going to learn on the back of this sheet. The sum of the interior angles of any polygon can be found with the formula 180 times n minus 2. That's sum of the interior. That's all the angles added up. So there's lots of ways they can ask questions referring to that. We're going to do these first 3 together. Find the sum of the interior angles of an octagon. This is probably the most basic way of applying this formula. If it's an octagon, what's n? What's n if it's an octagon? 8. Good. So we're just going to do 180 times 8 minus 2. Because n minus 2, let's write it here, 180 times n minus 2 equals the sum. So 180 times 6, remember order of operations, you have to do what's in parentheses first. And 180 times 6 is 1080 degrees. That's the sum. So in any octagon ever, no matter what weird shape it could be, if it has 8 sides, you add up the interior angles, and it's going to be 1080 degrees. Again, we're talking about convex polygons here. Number 2, how many sides does a polygon have if the sum of the interior angles is 1980? So now they're asking you to find n. Find the number of sides. Again, use your same formula. The sum equals 180 times n minus 2. Where does the number 1980 go into this formula? Where does that go in for? Jack? So number of sides minus 2 is 1980. What is 1980? The sum, right, exactly. So the sum is 1980. N is what we're looking for. So now we need to solve this equation for n. You could distribute, but I find it easier just to always divide by 180. Then automatically that gets canceled out. But you could distribute and solve that way. When we do 1980 divided by 180, we get 11. And that equals n minus 2. Add 2 to both sides, and n is 13. So the answer there is 13 sides. Okay, or they could give you a problem like this. Find the measure of angle y. just going to call it y. Well, we've done problems like this before with triangles. They give you two angles and you have to find the third missing one. And you know that the three angles add up to 180. First thing we have to do is figure out what these angles add up to. Well, there's 1, 2, 3, 4, 5 sides. So the sum of the angles is going to be 180 times 5 minus 2. So that's 180 times 3, which is 540. So these angles add up to 540. 540 equals 110 plus, don't forget the 90, plus 120 plus 150 plus y equals 540. Well, when you add all those up, all these added up turns out to be 470. So 470 plus y equals 540. Subtract and you get your y. The measure of angle y equals 70 degrees. Okay, so try A, B, and C. A, B, and C, try them on your own. They're just like the three we just did, so you can refer back to those, and then we'll come back and check our answers. Their answers. Okay, so check your answers for A, B, and C. And we will move to the back. This is relating to hexagons and honeycombs, but I want to get down to the real important piece here is that the sum of the exterior angles in any polygon is 360 degrees. So, like I said, all of these problems come down to the same two facts. The sum of the interior angles is 180 times n minus 2, and the sum of the exterior angles is 360. If they ask us, what is the measure of an exterior angle, meaning one exterior angle of a regular nonagon, we have to use this fact that all of the exterior angles add up to 360. If the sum of the exterior angles is 360, how could we get what one exterior angle is? What could we do? Divide it by the number of sides. In this case, the nonagon has 9 sides. So you're going to get 360 divided by 9 gives you 40 degrees for each exterior angle. Once we have this answer, that each exterior angle is 40 degrees, how would you solve this question? What is the measure of each interior angle of a regular nonagon? So same shape. How would you get the measure of each interior angle? What would we do? It's back on. Okay, so you could go through the trouble of using the formula 180 times n minus 2 over n to get each interior angle. Or we can remember that the interior angle and the exterior angle form a linear pair. So by the linear pair postulate, the interior angle equals 180 minus the exterior angle. So 180 minus 40 is just 140. So each interior angle of a nonagon is going to be 140. So remember that when you're doing problems that involve them giving you an exterior angle to find an interior angle or to find the number of sides, it's going to be easier to use exterior angles than it is to use interior angles. Why? Because interior angle formula is more complicated. It depends on the number of sides. And if you don't know n, it makes for some algebra, right? But the exterior angles is always 360. It doesn't matter how many sides. So let's take, for example, let's say that I tell you that the interior angle, one interior angle of a regular polygon is 150 degrees. And I want you to find how many sides this polygon has. Okay, that's another question they could ask you. Here's the measure of one interior angle. So if I have a polygon, I don't know how many sides it is, but I know that one of the interior angles is 150. If they give you interior, immediately try to figure out exterior. So much easier. What's the exterior angle? 30, right? Because that's to add up to 180. So if the exterior angle is 130, and what's this? I'm sorry, 30. What is the sum of the exterior angles? Always 360. So if we do 360 divided by 30 degrees, that means there's how many exterior angles? 12 angles or 12 sides. Okay, we're actually not going to do this homework assignment. You're going to do the packet that I